Hello everybody and welcome to another one of these geometry of pattern session things. And yeah, this live format might not be the best because if you're watching this live it's very hard to watch. But you know, if you're watching the recording, hello and welcome. If you're live, hello and welcome. Today we're going to look at, hi, I'm Kami Kyodai, and today we're going to look at this very interesting, very important topic that I like to call the sacred ratios. So these are patterns that come up in the three main categories for Islamic patterns. So we're going to see how these tie into Archimedean times. We're going to see how these tie into quasi-periodic patterns. And I'm also wearing my pajamas today, but you can't see that, thank goodness. And we're going to see these irrational ratios. And they each pertain to a specific sort of a symmetry, and they all have different characteristics, and they might share some nature of them are similar, but each of them has their own little character. So today it is Sunday, it is 3:24 on the 24th of January. We have a quote from Hunter Thompson. Also, there's a variation on it that's more like a Mohammed quote. That's trust God, but tie your camel. This is Hunter S. Thompson saying, call on God, but row away from the rocks. So I don't know. I was like getting this ready, and I have to not forget this. But we might just, derive it. Also working on like the ratio and how these things work, but we're going to start from the beginning. So you might be familiar with the golden ratio, and you might be familiar with the silver ratio. But the thing that you might not be familiar with is the silver ratio. So we're going to, before we go into the quadratic formula, so we're not going to talk about the quadratic formula, we're going to use the quadratic formula, which is different. So let's just call this topic for now the sacred ratios. So let's start from here. So you might know about the golden ratio. The golden ratio has a relationship closely tied into the pentagon. Actually, let me use another color for this to separate it from the... So, Kepler famously said that the golden ratio was the jewel, the Pythagorean Theorem was the crown jewel, and what was the quote? It's a Kepler quote. Like, the golden ratio was like this crown jewel, and the Pythagorean Theorem was another kind of precious thing. The golden ratio is 1 plus root 5 over 2. People might know this more to do with Fibonacci, right? This is the Fibonacci sequence. So the Fibonacci numbers, I guess you could call them this. You can approximate this ratio by doing this little fun thing of adding like numbers, right? You can go like, you start with two numbers. People usually choose 0 and 1. So these are our first two numbers. We add them up. We get a number. Then we add the result, the last number from the higher number from the last equation, last thing, and we add the result to it. And now we add this last one to the result we got, the bigger one to whatever we got. And you might be familiar with this, you might not be. I think this is a very beautiful thing. So the way that this becomes this is we take one of the bigger ones and we divide that by the previous one. So we have here the 1, 2, 3, 4, 5, the fifth Fibonacci number divided by the fourth. And this would be something like 1.6 something. We could do this, but 1.6 something, I don't know. But as we go higher down the sequence, the more that this approximates this. So it's interesting to think that this is a number. This is not it's an irrational number. This is not 1.6 whatever it is, 1.618 whatever number. That's not it. Because no matter how many numbers we go down the sequence, we will never really reach what this represents. So this is the number, 1 plus root 5 over 2. If you want to construct, actually this number has a lot of history, because we actually as human beings find this a lot in our own body. So our hands actually have this golden ratio inside of them inscribed. Why do my fingers look like that? Anyway, but like the ratio between each of this part of our fingers is also, it can be the golden ratio, and that's actually was found by a surgeon. A person walked into a surgery room with bird shot in their hands, and so they had to do an x-ray, And I don't know what he was on that day, but he just kind of like saw the x-ray and was like, huh, what is that? Like, he just saw that it was very symmetrical, like, because it was full of birdshot. There were a lot of like points on the hand. You know, birdshot is just like a shotgun, just a blast. So I don't know, he found that the hand was that, and so it turns out that our whole body is just like golden ratio. So this can be found in the human person quite a bit. And it might be because we're so anthropocentric that we tend to just look at a spiral or anything in nature and go, oh, that's a golden ratio. It isn't. Most of the time it isn't. For human beings, it tends to be, but not for all the sequences in nature. So we are kind of like anthropocentric even in the beauty of nature. But if you wanted to like also see this as a geometric expression, there's a very cool way of doing it. So we're going to use Kepler's little phrase here of the Pythagorean Theorem, and we're going to think about it. Let's get the root 5. So let's get that expression. So we know that, well, we don't know, but we have this little thing, the Pythagorean Theorem. So the Pythagorean Theorem, I'm not going to go into it too much, but there is a very cool video on YouTube, which I forget right now, that pretty much demonstrates how this expression is actually about how the right triangle is an area adding machine. So if you have this, and you have any figure here, in this case let's put a square. You might already know this. Like, I don't know who I'm talking to. This could be kids, this could be adults, it could be people that know geometry, this could be people that don't know geometry. So back in the back thens, they used to not do it like this. They actually would be more focused on area. So they would say something like Q1 to represent area 1, and then area 2 is equal to area 3. But it's more like an area adding machine. So if we have this filled up with something and this filled up with something, that we can add them together, and it's going to be this square. But this could be just as well a semicircle as it could be, you know, whatever. It could be whatever. As long as the figure we have here is similar to the figure we have here, as in it has the same ratio or proportion or whatever, then this one will also have that sum of area. It doesn't have to be a square. It just happens that it works really well, just as well for squares, but it doesn't have to be a square. So okay, we have this little bit. So let's just suppose that it's true. We can prove it for, can we prove it? I don't know. Math people, let me know if we can prove this. I just take it for granted because it's just taught down, and you know you can actually demonstrate it in very different ways. But it only works in flatness world. It doesn't work for a spherical world. It doesn't work for a hyperbolic world, but it works very well for flat world. All right, so we have this, and we want to get root 5. So it just so happens that, you know, we could also say that the square root of A plus the square root of B is equal to the square root of C. So we want to get root 5 over here, so this has to be equal to root 5. And so which two numbers add up to 5? We have square root of 1 and the square root of 4, right? So this square root of 4 is 2, and the square root of 1 is 1. And well, doesn't really, this one stays, yeah, let's not do it like this. But this square root of 4 means that we're trying to, that this is the area of 4. So that's what a square root means. If you have a square with an area of 4, the square root of it is going to be what this line is. You might not know this, you might know, I don't know. I don't know what you know. But we have that. So we have a square with side length of 2 and a square with side length of 1. What is that? Well, that pretty much is a 2 to 1 rectangle. So if we have a rectangle here, that's just two squares on top of each other. So we have the 1 here, we have the 2 here. If we draw a diagonal line, this diagonal line is going to be, oh Jesus, this diagonal line is going to be root 5. 2 to 1, that's a root 5 line. So we're saying that 1 plus root 5 over 2. So, you know, this is a very just old school way of getting it, right? But if we had a compass, what we get with a compass is that in a circle, from the center to the circumference, the line is going to be equal here as it's going to be there, right? So any line from the center towards the circumference in a circle is the same from the rest of them. So if we put a circle here, and get this as our radius, and we start like drawing it and then when it intersects with this extension of the line, then it's going to be 1 plus root 5. And so we can like lift this up, we can extend this line, and it's going to intersect here. These are going to be right angles, you know? And then, because this is 2 and this is 1 plus root 5, if we wanted to make this unit length, we divide it by 2, so it would be like 2 over 2, so we want to get it to 1. And then this would also be over 2. So when this rectangle has a unit length, this width of it, depending on how you orient it, of course, it's going to be 1 plus root 5 over 2. So this could be a geometric way of expressing the golden ratio, which also spawned the Fibonacci numbers, or rather, from the Fibonacci numbers, we could get the golden ratio. So the golden ratio has very interesting properties, not just this, but also very interesting properties. For instance, we have the golden ratio, we usually write it down as phi. I don't know how to draw phi. It's like a 6, but it's not really a 6. But it's like a letter. It's a Greek letter, and the letter is phi. That's how we write it down phonetically. But it actually has a symbol associated with it. I think it looks like a 6. It's kind of like that. Kind of. I'm not good at drawing the Greek letters. Alright, so let me just erase this for now. So it usually happens that, you know, we get this expression for the Fibonacci numbers in terms of the golden rectangle. The golden rectangle being, you know, made famous by the Greeks. And, you know, it just happens to be that we have the golden rectangle, which is the 1 plus root 5 over 2 to 1 rectangle. It just so happens that if we inscribe a square here, the remainder will have the same ratio as the big square. So this was actually described also by Plato. But Plato described it verbally. He said that the big was to the small as the sum was to the large. So he's saying that if we have, we could even do it with lines for this case. But if we're saying that we have a small line and we have a long line, Plato was saying that the sum of them together like that, the ratio of the sum is the same, the ratio of the sum to the large is the same as the large to the small. And so what also happens is that, well, because we're sort of like inscribed in this way, this is going to spawn like this topic of the metallic ratios, but we're getting there. So if we have a square here, and we have the same ratio of a rectangle here, you gotta sort of imagine because of my crudeness. But it's sort of, because we have the same rectangle in this little bit left over, we could do again another square. And because the leftover is gonna be the same as the big one, we could add another square. And so we would get another square here, and then another square would be there, and then another square here, and then another square there, another square, another square. And so we have what we call the golden spiral, you know, made famous by whatever. You can choose many different sources, who made it famous, who made it what. You can even like go to bands like Tool, right? Like they're very inspired by this in one of their songs, but it just was, it's big. This is a golden ratio. Just look at a hashtag on Instagram, right? You're gonna find it. So Plato described it like this. The sum of the small to the large, what was it? The large is to the small as the sum is to the large. So there's this quasi-periodic thing that it's like the only one-dimensional quasi-periodic pattern we know of. And it goes a little bit something like this. We have two lines. We have a big line and a long line. And we actually name them. We say here this is long, L for long, and here an S for short. And we're going to get into them. And so on the next sort of level, the long is going to include a short. So no, rather, the short becomes long and the long becomes long and short. So on the next level, this becomes a long and a short becomes a long. And so next level, long becomes long short becomes long becomes long and short. I'm not good at managing several markers here. I saw this guy on YouTube who teaches math classes, and he does this thing where he's like holding several pens at the same time, and shit. I'm not like that. But we call this a musical sequence, by the way. So as we go further down the line, as we go further down the sequence, I'm not using blue. As we go further down the sequence, we see that there's a little sequence happening: LS, LSL, LSL, LS. And so we go that L becomes, so as we go deeper, we say that L is, well, sort of like not equal to, but like kind of, like as we go deeper, and like that. So when we go to a level deeper, S becomes L, and L becomes LS. And so it keeps spawning, it keeps going down, down, down. So this is what we would call a musical sequence. And this is very interesting because it actually pertains to the way that Islamic patterns and quasi-crystals are ordered in the 10-fold world. But yeah, so this is a one-dimensional quasi-periodic pattern. It's a very beautiful thing. You can like take it down as much as you want it to go. Another thing that's very cool about the golden ratio is that the inverse is the same as 1 minus the, so if we say that 1 over, I want to write down the symbol, but I don't know how to write it, so I'm just going to write the whole thing. So 1 over 1 plus root 5 over 2 is equal to 1 minus root 5 over 2. So this is a very cool thing where the inverse of the ratio has a relationship to the ratio itself. In this case, that's a 1 plus and then 1 minus. Alright, so I'm going to leave the rest of it to you, but just know that we also can use geometrical figures to understand, or at least sort of like intuit where they come from. So the golden ratio pertains to fivefoldness. So it just so happens that if we have a pentagon and we draw the diagonal line of it, that line in relation to the unit, so if this is 1, then this line is going to be 1 plus root 5 over 2. So this is a little bit of where it might come up in Islamic patterns, because this sequence also will happen that if you keep drawing the line, you're going to end up with the 5-2 star, and inside of it is going to be another pentagon. So it sort of like has itself inside of itself infinitely. You can always find itself more and more deeper, and it just keeps going. You can even find that on this leftover of the star, you can actually draw a pentagon there. You're going to have a little bit left over, but it doesn't matter. Even if you if you were to fold, if you were to cut this and have this little space and you could put it together, you would have like a little cap. And it's a very beautiful little shape. And with origami, it's very accessible. So we have the golden that's inside of the 5-ness. All right, cool, right on. We got to move along though. I don't know what time we started, but we got to move along. All right, so we're covering the golden. I'm going to leave the red for the golden. I'm going to stay with the green for explaining shit. And now I'm going to use the blue for the silver, even though the silver or whatever. All right, yeah, this is going to make sense as I'm drawing along. So, silver, 1 plus root 2. This is the silver ratio. This one has also the interesting property that the inverse is also going to be simply, so 1 over 1 plus root 2 is going to be equal to 1 minus root 2. So the inverse of the sum is the 1 minus it. So we have like the constant of 1 and then the irrational value of 2. But these are not separate numbers. This is the number. And this is 1.141, I don't know, something. It just keeps going and going and going. But we get it like this. So we can also use the Pythagorean Theorem for this one. Where will we get the root 2? So if we said that, square root of a plus square root of b is equal to the square root of c, and we know we want to get 2. So which two numbers add up to 2? We have 1 and 1. So we're pretty much just like a single square and the diagonal of that square. The diagonal is going to be root 2. So we apply the same thing of using like circles, and you can think of the circles as being like, completely related to compasses, but circles really. Not about the tools, we're about the objects. So we have that as root 2, that's not understood, but root 2. If we get a circle, this is going to be the radius. We extend, line goes, makes contact, line extends, comes up in a right angle, perpendicular right there, like this one is. We have a rectangle, and we can have this be 1 plus root 2, and this is going to be 1 because it's a square. So that is the silver rectangle. Now, there's this thing about the silver ratio that is like a consequence of the Europeans having their system of paper size be the A. So that's also where this beautiful thing comes into play. So if you're in Europe, you might be, or any other place that's not the United States or Mexico. The United States has this like it's insane, dumb, stupid idea of like having their paper size be related to the size of the typing machines from the 18th century, which is nonsense. So in my case, I'm in Mexico, right? So if I go out and buy a piece of paper, the paper is going to be 8.5 inches by 11 inches, which is nothing. Like there's no relationship between these numbers. Somebody once tried to tell me like it was a golden ratio number. Bullshit. It's not. It's nothing. But what it is, I don't know the size for the European, but what they do have is that the short side is 1 and the long side is √2. So if you're in Europe and you're going to have like this, now depending on which size it is, it's going to be either A4, A3, A2. What's beautiful about this relationship though, is that if we split it in half, right in half, then this one becomes √2 and this one becomes 1. Like the ratio remains. So if we keep cutting this, so now this one's √2 and now this one's 1, and if we keep going on, so this is how the A system works. It's just a matter of dividing in half. So if you're worried about like propaganda, right, you have like a sheet or a pamphlet you want to just like throw out of a plane so everybody has it, you just have to fold it in half, right? You can use this beautiful thing. So for propaganda, the √2 or the A system is beautiful. But just in general, right, for propaganda, for printing purposes, A system is beautiful and has to do with the silver ratio. So you will find in many, many instances that people will call √2 by itself the silver ratio. It isn't. It's the silver ratio kind of thing, but it's not the true silver ratio that we're concerned about. We're concerned about the sacred silver, not the whatever. This is a very beautiful object though, the √2, because in mathematics you will usually come across √2 to try and demonstrate why it's irrational. Like it'll be about irrational. If you're about crazy Hollywood bullshit, you can like look up Cuba Goodwin Jr. was it that guy? I don't want to burn nobody, but this actor. I forget his name, but it's not Cuba Goodwin, it's this other guy. It's I don't know, but he's like a crazy Hollywood actor, and he was like going on about like, man, I proved that √2 is rational and shit, like some dumb thing. So √2 is not rational. So what does irrational mean though? I don't want to curse too much, I don't want to draw that out, but what we're saying is that there is no two numbers, so there's no fraction of numbers that can express what √2 is. And we can actually like go over the process. I'm not going to go into it right now. You can look it up. Like it's a very famous mathematical problem. Pretty much like demonstrate why this isn't true. So if you want to just like from this video start to go down that road, you simply have to take this into account. Like demonstrate that this is possible. You won't be able to, but you're going to have a nice time. Because this is even, so one of them has to be even, but it's irrational, so which one isn't even? So it's a nice little contradictory statement. Not contradictory statement, but it's just an irrational thing. So this happens to be like that. Prove it, go figure it out. It's a you thing. But it is also what makes the imaginary world work in mathematics a little bit. Because there is no way to name this number except by using √2. There is no other way to say √2 but to say √2. There is no other way. You can say 1.1, but you will never actually be able to say the full extent of this number. But anyway, we have this. And now we've constructed the silver rectangle. Beautiful, right on. So, what does a silver rectangle have for us? Well, if we have the silver rectangle, and we start inscribing like, square here and square here. By the way, if anybody ever says that √2 is rational, you smack them and you give them a math lesson. Don't smack them. So anyway, if you have these two squares there, the remainder rectangle in between will be the same ratio as the big rectangle. So you can keep this going, and you would have another two squares and a rectangle left over, and you can keep this going and have 2 squares and a rectangle left over, and have then 2 squares and a rectangle left over, and it keeps going. And this is a silver spiral. It's 2 spirals that will never ever touch. They're side by side, but they never ever ever touch. They just keep going infinitely toward the center, but they never actually reach and they never touch. It's a very beautiful kind of like romantic love can be story. I like it. And you might see videos on what was it? It's just like gravitational waves, right? So there's this thing that Einstein theorized would happen. So if space-time is actually curved, then there would be like this instances of like that actually bending, like so much force and energy somewhere in the universe that actually like that could bend. So they had like these, I don't know, I'm not gonna go into, but gravitational waves, look them up. And the pattern that comes up, to me, looks similar to that. I'm not gonna be one of those like, oh, it is, I don't know, but it looks like that, kind of like two spirals, like meeting, never meeting, and then they meet, and just enormous amounts of energy. So yeah, silver ratio, the silver rectangle. What else about the silver rectangle? Well, it does have that thing of this is where it gets tricky, because you see these names are not trivial. There's this equation called the metallic ratio formula. So it kind of works like this. So in the metallic ratio, the silver ratio comes up in the form of 2 plus root 8 over 2. These are the same, by the way, because this root 8, I don't know if you know about factor trees, but if we have a square root of 8, you get the factors from it. We have a 4 and a 2. 4 is a square because it's made up of two 2's. So this one, we can take out of the radical, and we can express root 8 as 2 root 2. So we're saying here that this is 2 root 2 over 2. Oh shit, yeah, no. 2 plus 2 root 2 over 2. And this is equal to 1 plus root 2. And 2 root 2 is equal to root 8. Why am I saying this? Why am I saying this? Because the metallic ratio formula is sort of where it gets up. So we have n plus 5 over there, so it's the square root of 4 plus n squared over 2. This is a metallic ratio formula. So I want to get this out of the way. By the way, there's more to the silver ratio than I showed you. There's also something called the Bell numbers. The Bell numbers are, so there's like, I think there's 2 sets of numbers that you can get from the silver ratio. The Bell numbers, and there was another one that I forget right now. And there's like the video on it, you can also look it up, where they talk about how it's like the Fibonacci. So instead of the Fibonacci, the Fibonacci. And the Fibonacci sequence, I'm sorry that I'm like jumping around, but it's kind of like the same thing, but it goes like 0 plus 1, but it multiplies one of them. So it's not just like this, but I forget right now, I shouldn't even talk about it if I forget. But I think it multiplies this one and then adds that multiplication. This is a nice number file video, look it up. I'm not into it right now. I don't remember the sequence, but it's called, usually people call it the Fibonacci. So what point is, alright, one last thing before I get into metallic ratios. I'm sorry, as much as I am prepared, I'm not, right? So the silver. If the golden is in the pentagon, where is the silver? Silver turns out to be inside of that octagon. If we have an octagon, like so, and you know, this isn't even going into the rum theory. Not the rum theory, but just like rums in general, because there are some beautiful rums here. So okay, we have the golden, yeah. And so this diagonal line is 1 plus root 2 when this is root 2. So there is like this relationship between the octagon and this diagonal line. It's not strictly like if this is root 2, no, what was it? Yeah, it is like this. I think it is like this. If this line is 1 plus root 2, then this unit length is root 2. I think people say that this is 1, but I was doing the math and I don't think it worked. Or maybe it did, I don't remember. Maybe it is 1. Maybe it is root 2. I don't know, I was doing it today and I found that it was root 2 and not root 1. I might be wrong, I might not be, because if we do it like this, then this becomes root 2, and then this becomes 1, and then this becomes like that, so this becomes 1 as well. And so we have 1 plus 1, then what is this? It has to be that if this is 1, then this is root 2. But if then this is 1, then that's root 2, right? I mean, just like that, we can get it. So when this is 1 plus root 2, the unit length is going to be root 2. What are you going to do? Alright, so we have that the octagon has a very close relationship to the silver. So, okay, so this is when this is 1, but the octagon, am I using, no, I'm using blue. So again, like this is where things get tricky. The next number is where things get tricky. By the way, folding these is very much fun. I love to fold this, I love to fold that, and not get into the rums right now, but there is a lot to do with rums. Again, not going to touch that subject right now. Leave that for another time. So, okay, so then there's this bias, right? We're saying the numbers. So then a usual question, and one might come up as well, what's the one for 12ness? We're getting the 5ness, we're getting the 8ness. What is the other example of pattern that comes up? 12ness. So naturally you're going to think, well, it's going to be the bronze, of course, right? And it's going to be about 3 squares. It isn't, but I'm going to show you why that bias happens. It's a very exciting thing, and when I discovered it, I was like, oh my god, math. But it goes a little bit something like this. So n plus 4 plus n squared over 2. So let's plug in values. So whatever n is how many squares you get to have before you get another bit that has the same ratio. So if we plug in 1, we get 1 plus 4 plus 1, so that's 5 over 2. So we're saying that this rectangle is going to have 1 square, and then the leftover is going to have the same ratio as the full rectangle itself. Okay? So if we plug in 2, I'm going to use another color. If we plug in 2 plus 4 plus 2 squared, that's 8. Right? And we saw that this is 1 plus root 2. Okay, so this is going to have, what does it mean? It means that we're going to get a rectangle that has 1 square, 2 square, that's not a square. So 1 square, 2 square, and then the leftover bit, again, not very good representation right now. And then the leftover is going to be the same ratio as the full rectangle. So 2 squares and a rectangle of the same ratio, 2 plus root 8. And then there's the bronze. By the way, beautiful thing about this is that you can see that the same, like the formula itself has a clue as to how you can construct it. So let's just plug in 3. We're going to see how to construct the bronze, even though that is not pertaining to the sacred ratio. Bronze is not sacred, but I'm going to show you anyway. So it's 3 plus 4 plus 3 squared. So 4 plus 9. What's that? 13. 3 plus root 13 over 2. You think like, well, root 13, how am I going to get it? This is your clue. I'm going to put like a little tower that goes 2 to 3. So if we were to follow Pythagorean theorem and get this diagonal, like what is this diagonal going to be, right? So we get 2, that's a 4, area of 4. That's an area number. Maybe I should write it with another color. Or rather, I'm going to write it like 2 squared. And this is going to be 3 squared. No, 3 cubed. 3 squared. So 9 plus 4, right? So that's 13. So then this diagonal line is going to be equal to the square root of 13. This green line right there. And so by following our sort of system that we had before of getting a compass, like, equating this line over to this over here, like spreading it, and then we would get like a rectangle. Or rather, no, because it's 3 plus 13, so we're not spreading it that way, we're spreading it that way because it's 3 plus, so 3 is here. So we want to get the line on the 3 line, so it's almost like this green line, imagine that this green line is the same as that line. So then this also root 13. And then we keep this going, we equate it to that, and I'm going to take this away, and take this away. Rather, I'm going to keep this 2, and keep this 3, and so 3, 2, and then root 13. And so this rectangle will be the bronze rectangle. Now you might think, well, bronze has to be there, right? It isn't. This rectangle though, will have the property that you can find 3 squares and then a bit. But it's not anything to do with Islamic patterns. People try to like plug it in, but it's fucking worthless, man. I tell you, it doesn't work. So I'm gonna teach you the true next one. It's called the platinum ratio. And it is in the literature. It's not in the literature you might expect, but it is in the quasi-crystalline literature. And it's called the platinum ratio. But it's not a metallic ratio. It jumps the boat. So this is the bias, right? So people might think like, well, we found the formula for the sacredness. No. God is higher than us, right? God is way, way above us. We've got nothing on God. So the next one is the platinum ratio. And this actually comes up. If you Google it, it won't come up. You have to really dive deep into the quasi-crystalline literature to come up. If you're interested, if you're actually watching along and you're interested about what is the platinum ratio, send me a message or join the Discord server. There's several articles that I've uploaded there that talk about this. Anyway, the platinum ratio, what is it? How can we find it? I'm just going to give it to you. Raw, going to give it to you. 2 plus root 3. That's the platinum ratio. We still have to get into the quadratic formula thing. I don't know how much time we've gone. Doesn't matter. So this is a platinum ratio. So where can we find this? Well, it turns out that this root 3 comes up a little bit in the form of hexagon. So if we have a hexagon, this is not the proper way to put a hexagon. If we had a hexagon like this, the height of it is going to be root 3 when this is 1. So that means that if we put a square here, and this is also going to be 1, and we put a square here, and this is also going to be 1. So the full length of this rectangle would be 2 plus root 3. Now, wait a minute. What is this? What is this shape? What do you mean putting squares on hexagons? What are you talking about? If we keep this going, though, if we put more squares in this hexagon and keep tallying it up, it's not a very good drawing, but you gotta bear with me. You gotta imagine, you gotta use your imagination, or if you're familiar with the compass and straight edge, go ahead and do that. By the way, this line might not be drawn there the best. This line might benefit more being there. We can complete this shape, and this actually has unit length all across. And this actually is not only a Archimedean tiling, but it's a regular polygon. This is a dodecagon. So it means that the platinum ratio is inside of a dodecagon. Now, to properly draw a dodecagon, I could use that, but I'm going to go ahead and just draw it like this. So 1, 2, and then... Oh, shit. See, here's the way I usually do it. I draw 6 points, and then I draw 6 points in between. So 6 points, 1, 2, 3, 4, 6, like that. And then I connect those points. And again, you gotta bear with me, man. This is not a very good dodecagon, but you gotta get the idea this is a dodecagon, a 12-point regular polygon. And if we go and draw a line that's gonna be from here to here, almost, then this line is going to be 1 plus root 3. And then you might be asking, well, what is this? If this is 1. This actually is 1, actually. This is 1. In this case, this is 1. This is 1, and this is 2 plus root 3. And I was doing some math regarding some other thing that I'm not going to go into right now, but I'm curious now if this actually is root 2. I think this actually is root 2, and this actually is 1. It has to be root 2, because, well, I just showed you how it was. Has to be. Just has to be. Yeah, it just has to be. Yeah, so we have that in the case for the platinum, we have a dodecagon, unit length on the edge, and the line that goes up is 2 plus root 3. We see it here demonstrated, how we can put squares and then a hexagon. And so the 2 plus root 3 is the true platinum ratio. 2 plus root 3, so very beautiful. The properties for this are very weird. But it does have this thing that if you actually inverse it, so if you put 1 over the inverse of 2 plus root 3, you would get 2 minus root 3. So it does have this property as well, just as the silver and golden have. But it has different sequences as the golden and silver. First instance, it's not to do with pure squares. This one actually includes a hexagon in the mix, and it makes a lot of sense. It has to have the 12ness. But, okay, so this is where we're going to include or talk about the quadratic formula. And, you know, I would love to talk more about the platinum ratio, but I know very little about it. It's one of the more mysterious ones. It's so fucking weird. You really gotta like dive very, very deep into quasi-crystalline structures and like all types of weird stuff. Because you're combining symmetries on this one. And actually, if you go into Richard Henry's course for his journal, he was just teaching a pattern that it's inside of this Archimedean tiling. By the way, if you've been paying attention this whole time with the classes we've been giving, what would this Archimedean tiling be? So we go to a point and we say that, well, we can write this sequence as a 6.4.3.4, because it goes hexagon, square, triangle, square, hexagon, square, triangle, square. So this arrangement is a 6.4.3.4, and it's where the platinum ratio is found. So it happens to be that way. I would love to talk about it more if I only knew more. But it does have this property, so there's that. And now we're going to talk about, well, I'm going to include it there on the board, of course. And then we're going to talk business. So let me see how I can draw this thing though. I'm going to try to draw this one in green. Let me see now. So it'll be like this, and then jumping around like this. It has to be a 6, right? So 1, 2. Yeah, this one's hard to draw. So there's my 6 points, and well, I wanted to actually have it rotated, so I'm going to try and do that. Because I want to have, no, I'm going to leave it like it is. It is what it is. So 6 points, and then 6 points in between, and then these get connected. And then we have a line that goes, well, I'm going to change it up a little bit with the colors here. This line goes up like that. And well, actually, I didn't talk about it, but there's also the platinum rectangle. And it's simply just like completing this line right there, but I'm going to talk about that. Got the silver, the gold and the silver and the platinum. 5, 8, 12. So there's even like this nice little sequence, right? 5, 8, 12. Pertaining to 5, 10, whatever multiple of 5, pertaining to 8, whatever multiple of 8, and 4, just so happens, and platinum, whatever multiple of 12, and just so happens 3 and 6 are in there, and 4, use 12. Yeah, just a quick little drawn platinum ratio rectangle, so it's going to be 2 plus root 3 to 1, and so what this means is that we have here 2 squares and then the height of a hexagon. But I forget now, man. I forget like how to make it happen, because it's not, there's this beautiful sequence and I forget it now. It's a shame, but whatever, you know, sometimes it happens. But there's a beautiful sequence that you can get if you like play around with the way the light bounces around in this thing. So I'm gonna leave that for homework if you're so keen on it. All right, so now we're gonna talk about the quadratic formula and then we'll call it a day. Why? Because we're crazy. So it goes on to be that the quadratic formula is x plus minus b plus minus, because there's going to be 2 roots, the square root b squared minus 4ac over 2a. So that is a quadratic formula, and now we're going to find each of these ratios. Actually, I missed writing this one in. And this is 2 plus 3. And this is so now we're going to plug these in and try to find the quadratic. We're going to try to find the a, the b, and the c for those ratios. So, you know, I might just give the list, but we're going to actually do it this time. So let's start with the golden. I'm actually going to do it with I left my black marker outside, but 1 plus root 5 over 2. So we know that underneath is already going to be 2, so we have 2, so pretty fast. Where am I going to write this? I'm going to write this here. So I'm going to write a little list. I love lists. I'm going to write this. I'm going to change the order of this thing. Let me just go ahead and write this over here. And then here I'm going to write the quadratic formula just for reference, in case whatever. Minus b plus minus the square root of, I always want to put the 4 first, b squared minus 4ac over 2a. Maybe I shouldn't do that. I gotta get into like some graphic design classes or something. Nah, maybe not. I'm so lazy, man. Anyway. So we have that a. Oh shit. We want to find a, b, and c for the golden. So pretty fast we know that a is going to be 1. Has to be 1. And when we have that, it's going to be minus b. So it's 1, so minus b, so it's got to be negative b. So b is going to be negative 1. And then, well, we just got to find where the c is. So, you know, we plug it in. So minus 1 squared minus 4a is 1, so that's 4. We got to add up. So this 1 minus 1 squared is going to be 1. So we want to make it positive. When we make it positive, add to 4. So we simply add minus 1. And that minus 1 multiplied by minus 4 is going to make it so 1 plus 4, so that's equal to 5. And so with that 5, we now have 5 inside of the radical. And we have here our first set of numbers here. These are the numbers for the golden. The A, B, and C for the golden. So you can plug this into a quadratic calculator and you can get your quadratic solution for the ratio. That's a very beautiful thing. It's also very simple numbers. 1 minus 1. Although, because it's a quadratic formula, quadratic equation, is not 1 plus root 5, but rather 1 plus minus root 5. Interesting. Remember how if we either subtract it or add it, we get the other one. Right? So 1 minus root 5 over 2 is the same as saying 1 minus the 5. So yeah, this is a very interesting detail, this thing. But plug this into a calculator, yeah, whatever. Alright, so we cracked the golden. Now let's go to the silver. Silver is 1 plus root 2. We can take advantage of that. We already discovered how to get in the metallic because we don't have a number underneath, so it's going to make it difficult. So let's put a number underneath. So if we put a denominator of 2, we have to make it so it's similar. So we multiply this whole thing by 2, and we get 2 plus 2 root 2. But because it's going to be more complicated, we write it as a simplified form of root 8. 2 plus minus root 8. So 2, that's going to be the negative b. So we want it to be positive 2. So b is going to be negative 2. Actually, I should write with the green, right? It's all in my hand. Alright, so we have the minus 2 done. So we put in here, over 2a, so that's also going to be 1. Right, because 2 is positive, this is positive, has to be 1. Nice little list. And then we just got to find c. So let's plug in the 2 to this. We want to get root 8. So negative 2 squared, that's going to be 4, minus 4 times a is 1, so that's 4, times c. What do we want? We want 8. We want to add 4 plus 4, simply. We want to make this positive. So we, again, minus 1. It's going to make so this is a positive 4. Therefore, 8. So there we have the numbers for the silver ratio. 1, negative 2, negative 1. Beautiful. Right on. You can plug this into a calculator. You're going to see a very nice little sequence happening. And then finally, the platinum. Again, this one breaks the rules. By the way, there could be more. There could be like a 7-fold thing down the line, we just haven't found it yet. There could be like a 14-gon ratio, we just haven't found it. These are the only ones known to man. And these pertain to Islamic patterns, so these are like the language of God, it's just above what we can describe. So we have 2 plus root 3. Again, we want to make it so the denominator is 2, so we can very conveniently find it here. So we multiply the whole thing by 2, and that's going to be 4 plus minus. We want to put a 2 there. So what would 2 square root of 3 be? And we multiply 2 squared and we add that to 3, multiply that to 3. So 3 times 4, because that's what 2 squared is, it's 12. Because 12 the square root of 12, we can write it here for now. Square root of 12, we find the factors of 12 is going to be 4 and 3. 4 is a square number, we can take that out of the radical to have 2, 3. So, square root of 12 is what we're looking for. 4 to square root of 3. So, 4 plus minus square root of 12 over 2. Alright, so same deal. 4, that's negative b. So, that means that b has to be positive 4. No, sorry, negative 4 in order for this to be positive. Where's the green? So this is going to be negative 4. Then this one's going to be also negative 4. Well, we know that a has to be 1 because it's going to multiply by 2, give us a 2 that we want. So a is going to be 1, b is minus 4. What's c? Well, 4 squared, that's 16. So 16 minus 4 times a, that's negative 4. So 16 minus what is going to be 12. 16 minus 4, so we want this to stay negative. We want to subtract it. So we're going to leave it as is. We're going to leave it at 1, positive 1. So then 4 times 1 times 1 is still negative 4. So 16 minus 4 is 12. And there you have it. So little break of sequence there, you see? You see how the c is positive? And then this one's 4, and this one stays 1. But this would give us 4 plus root 12 over 2, which is the same as 2 plus minus square root of 3, which is the platinum ratio. Again, I'm not the one calling it the platinum ratio. I actually found this in an academic research paper pertaining to crystal structures, so I'm not pulling it out of my ass. But you can't Google it. If you Google it, you will not come across it. You gotta actually like dive deep. So yeah, I guess we can leave it at that for today. So we saw the gold and the silver, the platinum ratios, what I call the sacred ratios, and these again pertain to different structures and substructures of crystalline patterns, which in turn are about Islamic patterns, because Islamic patterns could be understood as crystals. We can interpret Islamic patterns exactly as crystals. We can say that. We can say that an Islamic pattern is a crystal. So crystals and Islamic patterns actually are part of like the same microcosm or macrocosm, whatever you want to call it. So yeah, we have the numbers on the quadratic formula. We found their ABCs, and you know this actually would have more geometric implications, which are again are very interesting. Plug this into a calculator, man. It's a lot of fun. This one will not be as symmetrical as these other two, but it does have its properties, and you know this more the mysterious ones. And if you're interested about any of these, the golden, you know, you're gonna find a plethora of information. But if you go to Ambigraphs and meet Kinosha's Instagram page or his website, you're going to find that he gives actually a course on understanding Islamic patterns through the silver ratio. So there's that. So check that out. I'm going to leave that on the board. If you're interested about the silver, I recommend that you check that out. I should write this differently. That's a arroba. I don't know how to say that in English. At. It's a plug for my friend right there, for Ambigraph, man. Very cool guy, mathematical friend, cool. Alright, so we have our numbers, we have our figures. If you want to know more about this, if you want to know more about the golden, you know, just, like research Kepler, I guess. Kepler doesn't have an Instagram page, but he does really, really like this. So if you want to go like old school, yeah, just check out Kepler. But there's again, like if you just go look for golden ratio, you're gonna find. The thing about the golden ratio is that we are so anthropocentric that there's gonna be things that are gonna be called the golden ratio, which are not the golden ratio. But I leave that to you. So, all right, we saw the thing that we wanted to see today. So congratulations to me and to you guys if you're following along. And yeah, so you know, stay tuned, enjoy. Hope you have fun. And you know, be mathematical with each other and have fun and whatnot. Yeah, fun, and mathematics. Keep your head straight and yeah, feed it. What else? That's it, man. That's it. So thank you. Take care. I'll catch you in the next one.